So,
what about ball spot?
okay.
Uh,
I'm
I'm
going to
do
do
some
some
graph theory,
which is
which
going
is
to
going to connect
the
the
linear
linear
algebra,
algebra,
the
the end of the linear algebra that I studied,
and
and
the
the
project
project that I
was
was working on.
and
And it helps
the
the
general
general
direction,
which is
machine
learning, math for machine learning, right?
So,
So
I'm
I'm
going
gonna
to
do some.
oh,
Oh shit, that's my water.
Inigo
there,
graph
graph theory.
That's it.
That's it.
Okay.
Okay,
You look
you
at
look at
me.
me. Okay. I need some water really quick. Okay, let's go. Monsieur. Okay, fuck. Delete it. Let's go back. Let's go back. Yeah. Let's brave new world. Okay. Ha ha ha. Funny.
Hello and welcome, my name is William and I'm super excited to bring to you this video series focused on graph theory. Graph theory is one of my absolute favorite topics in computer science.
Yeah.
Yeah.
You see a lot of very awesome algorithms, the whole field is very diverse and hugely applicable to real world applications. I think everybody should be able to learn, love, and enjoy graph theory. These first few videos are going to be ramp-up videos to introduce the topics of how we store, represent, and
I
use
love
graphs.
graph theory, man.
By the way, this
Love
whole
it.
video series will be taking on a computer science point of view of graph theory rather than a mathematical one. So we won't be covering proofs and so on per se. Instead, we'll be looking at algorithm implementation details and code. So what is graph theory? In essence, it is the study of properties and applications of graphs, which common folk or non-mathematical folks call networks. This is a very broad topic, and my goal with this video series is to teach you how to apply graph theory to real-world situations. Graphs can be used to represent almost any problem, which makes them so interesting, because they pop up absolutely everywhere. A simple problem that can be phrased as a graph theory problem might be, given the constraints in...
So yeah.
I mean,
இந்த மாதிரி problems இதுக்கு முன்னாடி நம்ம பார்த்திருப்போம். இங்க ஒரு I don't know what it's actually called. But another Christmas season நீங்க போயிருந்தீங்களா தெரிஞ்சிருக்கும். You're supposed to give a gift to another guy, and he's supposed to give a gift. It's all randomized basically, and he's supposed to give a gift to another guy. So let's say me over here, right? I'm supposed to give a gift to this guy, and this guy is giving gift to this guy. This guy is gonna give to this guy, and it's gonna have like all these like randomized. You know what I mean? You know. But at the end, some dude is gonna give a gift to me.
But
the thing is, this happened to me in real life. I remember giving a gift to a guy. It was like, let's say 500 rupees, right? And this guy, this bum-ass idiot, fucking fucked me up with the gift. It's like fucking 10 rupees or something, you know what I mean? Like, at least fucking try. No? I think it was like my 10th standard tuition, I think. This guy gave me like a gift for like 10 rupees, and I'm here over here. Whatever. I'm still like salty about it. It is what it is. After all these years, man, I have to bring it up. You know, I have to bring it up on this special occasion. Fuck you. Fuck you, bro. Fuck you.
In this
Okay, let's
how
go.
many different sets of clothes can I make choosing an article from each category? Of course, this could be phrased and solved using only mathematics, but the advantage to graph theory is that it allows us to visualize the problem using nodes to represent an article of clothing and edges to represent relationships between them. Another canonical example of a graph theory problem is a social network.
Again, nodes வந்து so
இங்க
பாத்தீங்கன்னா தெரிஞ்சிருக்கும் இதான் நோடு நோடுங்கிறது நான் சர்க்கிள் பண்ணியிருக்கேனே அதான் இது வந்து ஒரு ஆளா இருக்கலாம் ஒரு எதுனா இருக்கலாம் whatever the node can be. It can be a computer, a human, anything. edgesன்றது வந்து
the
the connection,
right?
right?
The
The connection,
this
this
line
line
that
that connects people. All metaphorical shit. You know what I mean? Like, we're all the same, man. We're all the same. Shut the fuck up. Shut your fucking mouth. Okay, let's go.
Order of friends. A graph representation enables us to answer interesting questions such as how many friends does person X have, or how many degrees of separation are there between.
You
this
don't
want to be
this
this
guy,
guy, by the way.
Now we have to
Fuck
talk about
a
different
loser.
types of graphs. There are many different types of graph representations, and it's really important. I mean, really important to be able to recognize what kind of
Again,
The most important, there are like two main different types of graph, right? Again, in the data structure algorithms வந்து பார்த்திருப்போம். One வந்து இந்த மாதிரி graph, you know, it has like a direction to it. Goes from one direction to another direction. Right. That looks ugly as fuck. And two, we have non-directional tree-like structures. I mean, it's not directional. One has direction, and another one doesn't have direction. And obviously, tree, it all comes under it.
Let's go.
Fuck.
graph you're working with, and especially when you're programming and trying to solve a particular problem.
Yep.
This type of graph is an undirected graph. It's the most simple kind of graph you'll encounter, and it is where edges have no orientation. That is, if there's an edge...
I
watched this video, by the way.
Graph. Nodes are cities, and edges represent bidirectional roads, since if you drive from one city to another, you can always retrace your steps by driving the other way. In contrast to undirected graphs, there are also direct graphs, sometimes called digraphs. In these graphs, you've guessed it, the edges are directed. So if we have an edge from U to V, then you can only go from node U to node V, not the other way around. In this graph, you can see that the edges are directed because of the arrowheads on the edges between nodes. This graph represents...
What is going on here? Like,
so an incoming...
Look at
my hand.
It's like
a snake eating his own fucking tail. You know?
Edge represents receiving a gift, and an outgoing edge represents giving a gift. Therefore, person E in this graph bought person B a gift. Person A bought themselves and person B a gift. And person F bought nobody any gifts and received none. So far, we've only seen unweighted graphs, but edges on graphs can contain weights to represent arbitrary values such as cost, distance, quantity, you name it. Weighted graphs come in both directed and undirected flavors. As a side note, I will usually denote an edge of a graph as a triplet, U, V, W, to indicate where an edge is coming from, where it's going to, and
U, V, W. Okay. Fuck. U, V, W. Cool.
So I think,
this thing over here.
So let's
say A, 2, C. Woo! Let's go.
What its weight is. Of course, with this notation, I also need to specify whether the graph is directed or undirected. Next up, I just want to have a quick chat about special types of graphs in graph theory. There are so many different types of graphs that I only had to select a few which will be most relevant for this upcoming video series. The most important type of special graph is definitely the tree. A tree is simply an undirected graph with no cycles. There are several equivalent definitions of a tree, such as a graph with n nodes and n-1 edges. All the graphs below are trees, yes, even the leftmost one, since it has no cycles. A related but totally different type of graph is a rooted tree. The distinction here is that a rooted tree has a designated root node where every edge either points away from or towards the root node. When edges point away from the root node, the graph is called an aborescence, or an out tree, and an anti-aborescence, or in tree, otherwise. Out trees are by far more common than in trees, from what I've observed. It is also fairly common for people to refer to a rooted tree simply as a tree instead of an in or out tree, but there is an important distinction there. Next are directed acyclic graphs. These are graphs with directed edges and no cycles. These graphs are very important and fairly common in computer science actually, since they often represent structures with dependencies, such as a scheduler, a build system, a compiler maybe, or perhaps more relatable university class prerequisites. There are several efficient algorithms we'll be looking at to deal specifically.
So DAG is the directed graphs with no cycle.
Oh, it's
directed. Right, it doesn't like have a cyclical. Either the physics நம்ம படிச்சிருப்போம் நினைக்கிறேன். We have like a closed loop of current flowing from, you know what I mean, this type of shape. You know what I'm saying? Like goes from this one. It's like a closed loop. But on a DAG, what is it? Directed acyclic graph, it doesn't have. It just goes in. You know what I mean? It all like has like a trend, so to speak, in one direction. It doesn't like go finish any loop.
Or
Or in other words,
a
a graph only has outgoing paths.
I mean,
I mean,
this
has an incoming path, but
like
let's take this graph, right?
The
The graph நீங்க பாத்தீங்கன்னா it has some input coming in
from
from this one.
But
other than that,
it
it doesn't
get
it doesn't the loop doesn't get finished, so to speak.
It
It always like goes
in
in one direction.
Same with
Same with this one.
This
This
only
goes in this direction.
This
This only goes in this direction,
so to
so to speak.
Okay.
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 Can't
Can't understand it.
such as how to find the shortest path and produce a topological ordering of nodes. A topological ordering of nodes is an ordering of nodes that tells you how to process the nodes in the graph so you don't perform a task before first having completed all its dependencies. For example, a topological ordering of class prerequisites would tell you to take intro biology and intro chemistry before taking a class on, say, genomics.
Oh yeah. Same with like the video games எல்லாம் பார்த்திருப்போம் நம்ம. The game that I used to play was God of War. It has like a skill tree aspect of it, which I'm trying to implement too
in
in my program.
So
it's like a
Class prerequisite.
it's
a thing where let's say double jump, right? Let this be a double jump. For you to get good at double jump, you need to know how to jump. For you to know how to triple jump, you need to learn how to double jump.
Right.
So let's say this skill should be, I don't know, jumping. This should be like a flying kick or whatever. Flying kick. You need to be able to do a double jump to do a flying kick. You need to be able to jump to do a kick. Right? That letter is needed for a kick. Comes from you will be able to jump.
So
essentially, if you want to do a flying kick, either you can go this way or this way. Right? And let's say another move where you can go more with flying kick. It's a flying spinning kick, right? No. It should be like, look at this. So it should be accessible by both. Shouldn't be like so difficult. Let's say this is like a medium skill and it's a tough skill. And it both can go through this. So this should be like a medium skill. And this could ideally be a tougher skill. So it should be like a difficult skill. Tougher, okay. Medium, tough, difficult. We can like go with that. Easy. Easy. Again, it's all like how we describe it, basically. That's the way that I'm going to do my own like move set for Jujutsu too. Some moves are easy on the body, you can like easily do it. So the graphs. I mean, it's not like predetermined like this one where I have to like fill the nodes and properties myself. I can just put my nodes out there and start doing connections. This is like a really tough way to do it. Yeah, let's go.
This would tell you to take intro biology and intro chemistry before taking a class on, say, genomics. This next type of special graph is a bipartite graph. It is one whose vertices can be split into two independent groups, U and V, such that every
U and V. So it was U, V, W. And it could be split by U and V. Interesting.
Edge connects between U and V. This is just a fancy way of saying that the graph is too colorable or that there are no odd length cycles in the graph. Often, a problem we like to ask is what is the maximum matching we can create on a bipartite graph? Suppose white nodes are jobs and red nodes are people. Then we can ask how many people.
Interesting. Unemployment. I know something about that one. Hey, aren't we all unemployed? If you really think about it, AI is going to take our jobs. Might as well learn about the graph theory underlying the structures of unemployment.
Can be matched.
Let's go.
In this case, there are a lot of edges in each graph, so I think the answer for both is 4. In general, it's not so easy if there are less edges, tougher constraints, and more conflicts. Bipartite graphs also play a critical role in the field of network flow, which we will talk about later. This last type of graph is a complete graph. It is one where there is a unique edge between every pair of nodes in the graph. A complete graph.
Bro, whoa.
We
can
have listed K1 through K6 on the bottom.
Look at K5, man. Listen. K5, brother, listen. This one. Christ is king, man. Christ is king. Fuck all of this shitty religion. Fuck this religion, bro. Fuck you. This is even demonic. Look at this shit. K6. Never seen this before. This one too, man, bro. What the fuck? So this is like a complete graph. So it has even number of edges. Every node. So this has 3. This shit also has 3. And all of this is like connected in a completed. Could it be? Can it be this way? I mean, it would be like infinitely long. If it's not connected, it'd be like infinitely long. Okay. Bro, this shit, not a lot here. Let's go.
And you can easily see how this scales when we add more nodes. Complete graphs are often seen as the worst case possible graph you could possibly encounter because of how many edges there are. So if you want to test your algorithm for performance, a complete graph is an easy way to start. One thing we're going to...
Why is it the worst?
Because of how many edges there are. So if you want to test your algorithm for complete graphs are often seen as the worst case possible graph you could possibly encounter because of how many edges there are. So if you want to test your
because it has lot of edges. Yeah. Makes sense. Yeah. When you like go like let's say K9. K9 okay. K9 க்கு போலாம் இப்போ. I'm gonna draw like 9 fucking graphs. So why the fuck not? Why the fuck not? 1, 2, 3, 4, 5, 6, 7, 8, 9. You can like already see how complex this shit is about to get. And bro, you know what I mean? Like fucking hell. But if it's not a complete graph, it could look something like a little bit more less complicated like than that. In nature, let's see, where do we see complete graph? Yeah, that's what I was thinking. Like, like a carbon molecule or whatever. You like see this kind of structure. Yeah, and fucking brain too. Crazy.
One thing we're going to
Yo, I don't think brain has like a. I think brain has, or else my fucking brain has some missing edges. Let's just put it that way.
Really cognizant about is how we're actually representing our graphs on a computer. This isn't just what type of graph it is, but what type of data structure what type of data structure are we representing our graph with?
Oh, look at he fucking froze for a minute. Telling you, bro, you can't trust these people. Yeah, the model of Udemy is like completely gone. Like who the fuck is gonna like pay for Udemy courses anymore? Bro, I don't want to do Java. Java's gay. You know. Fucking Python is everything.
Code for friends implemented in Java.
But why does he do Java? Like fucking piece of shit, bro. Give me a fucking shit. Let's see. Tree algorithm. V plus I complexity. Mathematics? What the fuck? You have a mathematics channel.
I
mean,
it
it is a mathematical channel, of course. Of course, dynamic problem 3, network flow playlist. Brother, it's just come on, brother. Data structure. It's all like data structures. Data structures gay. I don't like data structures.
Have a huge impact on performance. The simplest way is inside a 2D adjacency matrix. The idea.
Okay. Fuck. We have a 2D adjacent matrix, meaning what is an adjacent matrix? Bro, I should know what an adjacent matrix is. Did he cover what an adjacent matrix is? But anyway, I should know what an adjacent matrix is. He didn't cover it, but let's see. Did he cover it? I think he was about to cover some adjacent matrix. But what is an adjacent matrix? I don't know. You caught me red-handed over here. What is it? I don't know. Interesting. It could be represented in a matrix, huh? It goes here. Huh. Adjacent matrix. What is an adjacent matrix? It's a very simple way to represent a graph. Is it like what is an adjacent matrix? Bro, it's fucking hot. Feels good. Let's turn the shit on. They're on it. Yeah. It's a way to represent graph. Okay, it's just like basically matrices. I mean graphs being represented through matrix again. Does it mean it makes it useful with graphs again? Bro, that's what I'm saying. Like I've never heard what an adjacent matrix is. So, what is shoot it? Give me a second, bro. 1 second. Yeah, it's fucking up my noise. Okay. Should it be a symmetric matrix? Undirected, yes. So if it's a undirected matrix, it should be a symmetric matrix. If it's a directed matrix, why? Wait, what? Why? I don't get it. Why? If it's an undirected graph, meaning it's like a tree-like structure. If it's a tree-like structure, it has to be symmetric. Why? Who said so? Who said so? What? So let's say it's a 3x3. I mean, I don't know how it's represented, but let's say this node is These nodes are represented in 3 by 3 matrix. Why? Makes no fucking sense, G. Makes no fucking sense. Let's go anyway. Anyways.
Cell Mij represents the edge weight of going from node I to node j. So in the graph,
Node I to node j?
below, it
What?
doesn't have a huge impact on performance. The simplest way is inside a 2D adjacency matrix. The idea is that the cell Mij represents the edge weight of going from node I to node j. So in the graph below, there are 4 nodes, so I create a 4x4 matrix and populate the graph with the edge.
Bro, this fucking annoys me. What the fuck? What the fuck, bro?
Hello, and
Can you go full screen at least?
Full screen?
Like
Like what? Bro.
the cell Mij represents the edge weight of going from node I to node j. So in the graph below, there are 4 nodes, so I create a 4x4 matrix and populate the graph with the edge weights. If you look at the edge weight from node C to node D, you'll see that it has an edge weight of 2. So in row 3 and column 4 of the matrix, there is a value of 2. Note that it is often assumed that the edge of going
Okay.
inside a
Second.
representing our graph width, and this can have a huge impact on performance. The simplest way is inside a 2D adjacency matrix. The idea is that the cell Mij represents the edge weight of going from node I
Mij.
Okay.
Okay. Ij.
1
1
to below, there are 4 nodes, so I create a 4x4 matrix and populate the graph with the edge weights. If you look at the edge weight from node C to node D, you'll see that it has an edge weight of 2. So in row 3,
C to D. Edge weight of 2. Okay.
Okay. Bro, now I get it.
So
So when I go, oh shit, that's actually crazy. Let's do an example.
Let's
do an example of this one.
Wait. Okay. Is it
The
the
relationship is unknown.
A
A,
B
B,
C
C,
A B C
C,
A
A to B,
fuck C.
C.
So
So A to B is gonna be
A
A to B,
A
A to B. So A, B, C. A to B is gonna be.
I mean
it's
yeah,
it's unidirectional.
Does it
Doesn't mean
it's
it's just one.
Okay,
Okay, it's just one.
Okay, it's
It's connected.
B
to C
is
is also
can a
can a
nigga
nigga
live?
live.
B
B to C is also one.
but
But
B
B
to
to C,
what
what the hell? What the hell?
Now
Now A to B is one again.
B
B to C is one.
C
C to B
is
is
one.
one.
What about
What about
A
A
to
to
C?
C?
A
A to C is one.
Oh,
Oh, Kumbaya.
What do you
What do you know?
Kumbaya,
brother.
Kumbaya.
Kumbaya.
Okay,
Okay, let's add direction to it because it makes no sense.
It's
It's a triangle. Yeah, K3 is a triangle. I can tell. AB is gonna be one. BC is gonna be one. CB is gonna be one. And BC is gonna be one. And CA
is
is gonna be zero. What?
This
This is gonna be one.
but
this is gonna be zero. So what the hell, bro? CC is okay, whatever. Who gives a fuck? Who gives a fuck?
for the matrix, there is a value 2. Note that it is often assumed
Yep.
that the edge of going from a node to itself has a cost of 0, which is why the diagonal of the matrix has all 0 values. This matrix form has several advantages. First, that it's very space efficient for dense graphs. That is, graph.
Oh yeah.
Let's say we have like a 16 by 16 matrix. It's much more easier to like visualize. I mean, easier to put it in numbers than actually have it in. Makes sense. Okay, adjacent matrix is basically it needs to be a square matrix, right?
Okay,
adjacent matrix has to be a square matrix. Okay.
Graphs with a lot of edges. The edge weight lookup can be found in constant time, which is quite nice. And lastly, I would argue that it is the simplest form of graph representation.
That's good. Yeah, that's good.
On the downside, however, the main reason people don't go for the adjacency matrix as their first pick is because it requires v-squared space, which is a lot of space. In practice, graphs with 10,000 nodes or more start to become infeasible very quickly. The other issue with the adjacency matrix is that it requires v-squared work to iterate over all the edges of your graph. This is fine for dense graphs with lots of edges, but it isn't so great for sparse graphs, since most cells will be empty. The main alternative to the adjacency matrix is the adjacency list, which is a way to represent a graph as a map of nodes to a list of edges. The idea is that each node tracks all of its outgoing edges. For example, node C has 3 outgoing edges, so the map entry for C will track the edge from C to A with cost 4, the edge from C to B with cost 1, and the edge from C to D with cost 2. Notice that in the list of edges, we only need to track 2 things: the node we're going to and the cost to get there. We don't need to keep track of where we came from because that's already implicitly known. The nice thing about adjacency lists is that it is great for sparse graphs because it only tracks the
Bro, okay, let me like make a visual diagram for Jujutsu. That's what I'm interested in. So how do I represent moves in a matrix? How is it even possible? Okay, let's try to do something like that. So let's go triangle. Fuck. So let's go triangle. And we have Gilly. Right. And what else? Omoplata. Bro, this graph theory is perfect for Jujutsu because that's how it actually works. It's crazy. That's how actually it works. You know what I mean? So let's go from triangle to Gilly. We have. How do I represent the edge? What is an edge? Is it a high quality, high percentage setup? Or what is it? Omoplata. R and C, right? Rear naked choke. Or the back. I was just like thinking submissions, armbar. Right. Armbar. So how can I connect these things? Okay. Triangle to what the fuck is this? Gilly. Triangle to Gilly. It's a relatively easy. It's tougher. I mean, it's not tough. It's a better thing to transition. You could pull a higher locality, you can transition to that. Okay, it's easier. This is the best. Right, this is the best. Armbar to Omoplata kinda exists. Guillotine to Omoplata never exists. Right. And triangle to Omoplata. That's like one setup I can think of. That's like one specific setup that I can think of from the reverse triangle. But it's like, yeah, it's a little bit. So this is the, how do I represent this? So let's say this is 5, 1, 3, 4. We have 4. How do I represent this? I think it should be a 4 by 4. Triangle. Gilly. Omoplata. Armbar. Triangle, I think this is all 0, right? Diagonals.
So
triangle to Gilly
is
is
1.
1.
Oh,
It's 4. 4 and G looks the same. It's gonna confuse me. It is what it is. Gilly. Okay. Triangle to omoplata. Is that how it works? Is that how should I do it? Triangle to omoplata. I'm thinking in terms of. Okay. I should like also go this too, right? Gilly to armbar. What is Gilly to armbar?
Let's
Say
say
I go for guillotine. The guillotine fails, or let's not transition to an armbar now. Let's say go for an armbar. He stacks me up. I can't go for guillotine. So yeah, it gets complicated. Okay, triangle to omoplata would be 1. No. Wait.
This is
triangle to omoplata. Triangle to.
Okay,
triangle to omoplata would be 3. No. I'm not thinking. I was just okay.
It
It was a non-directional thing, so I think everything is going to be the same. Let's do a non-directional one. Everything is the same. Okay. Omoplata to Gilly. 0. Omoplata to armbar. I mean omoplata to triangle. 3. Armbar to omoplata. What the fuck? Armbar to omoplata. Okay, armbar to triangle. 5. Armbar to Gilly. 0. Armbar to omoplata. 1. And I need one more in my row. Let's make it another one. 0, 4, 3. Is that 3? 5. 4, 0, 0. 1. Okay, 3. 0. 5, 0, 0, 1. 0. Yeah. Looks perfect. Yeah. I made something. Let's go.
And doesn't allocate additional memory that you might not use like the adjacency matrix does. This also means it's efficient when iterating over all the edges. The main disadvantage to using an adjacency list is that it is less space efficient on denser graphs. Another subtle disadvantage.
Okay. Let's
allocate additional memory that you might not use like the adjacency matrix does. This also means it's efficient when iterating over all the edges. The main disadvantage to using an adjacency list is that it is less space efficient on denser graphs. Another subtle disadvantage is that it takes big O of E time to access a specific edge's weight, although in practice you rarely or if ever actually need to do this. The last representation I want to talk about is the edge list. An edge list is a way to represent a graph simply as an unordered list of edges. Basically, it's exactly what it sounds like, a list of edges. Assume that the notation for any triplet U, V, W means the cost from node U to node V is W. So for this graph, the edge list is simply a list of 6 edges represented as those triplets. This representation is very simple. However, it lacks structure, and that's why it is seldomly used. Advantage to the edge list is that it's great for sparse graphs, iterating over all the edges is super easy, and the structure is simple. The downside is that edge lookup can be slow, and you can run into memory issues on large graphs. Well, that's it for this video. Next video, we're going to be talking about graph theory problems. So thanks again for watching, and please subscribe for more mathematics and computer science videos. Cheers.
Okay, that's.
Hello and welcome back. My name is William, and today I'm going to talk about common problems in graph theory. A lot of problems you will encounter can often be reduced to a famous or well-known problem or some variant thereof, so it's important to familiarize ourselves with common graph theory problems and their solutions. Just before getting started, off from what we learned in the last video about representing graphs, I want you to think about how you would store and represent the graphs in the upcoming problems I'm going to describe. In particular, is the graph in the problem I'm describing directed or undirected? Are the edges of the graph weighted or unweighted?
So common graph theory problems. For the upcoming problem, ask yourself, is the graph directed or undirected? Are the edges of the graph weighted? What do you mean weighted graph? What is it? What does it mean? It's just a graph with each weight a number, okay. Edge just carries numbers sometimes, okay. Crazy. Can I... B... What does it call? Can an unidirectional graph be weighted? Could be. Absolutely, yes, I know.
Is the common use case a graph that is likely to be sparse or dense with edges. And lastly, should I use an adjacent matrix and an edgeless or some other structure to represent my graph efficiently? So one of the most, if not the most common problem in graph theory is the shortest path problem. Given a weighted graph, find the shortest path of edges from node A to node B. So if we pretend this graph represents a road system and we're at node A and want to get to node H, our shortest path algorithm should be able to find us a list of edges to follow that will lead us from A to H with minimal cost.
So why do I need the shortest path in Jiu-Jitsu? The shortest path could be think of as fastest way to basically, right? It gets complicated when the graph started moving the other direction because he has, let's say, I have a double leg, right? I have a double leg. He has a hip throw of a double leg, so I need to combat that. So I have a body lock pass, right? And he has a rubber guard, and I have a side control attacking game. He has a buggy choke. He has a buggy choke, right? I have an arm bar, and he has a hitchhiker escape. So it can get like a little bit like a game theory and like shit like that. So the short path problem. Why do I actually need it? Like where can I use it? So let's say in an arm bar case, right? Let's say an arm bar. Is arm bar a good example? No, okay. I'm thinking of let's think of a transitional thing where like I don't know. There's a lot of transition. Thinking of a lot of transitions. Let's say I go for a single leg to let's keep it simple. Okay, triangle to an arm bar to an omoplata, right? So this is the relation. It goes from one. It basically goes like this, right? This basically goes like this. So what is it? So if you really think about it, why do I need shortest path for this? Already have a path. So let's say I'm thinking about a move in a broader way. Where I need to talk in Tamil. Tamil is okay. Let's say the move in a பெருசா யோசிக்கிறோம். Okay. I can represent it in this way. Where there's directions. I can go one from another, or I can like represent it in. How am I going to represent all counters? So in like an obsidian, I could be like, okay, it's going to do this. Now we can do this. That's smart. That's smart. It's a little bit of a graphic. I was thinking, again, it's not really like a logic. It was just like a. I'm thinking about edges. Okay. Again, let's stop talking. Let's get into the video. Too much talking.
lucky for us, many algorithms exist to solve the shortest path problem, including a breadth first search for unweighted graphs, Dijkstra's algorithm, Bellman-Ford, A-star, and many more.
Breadth first search. Depth first search. Breadth first search.
As simple as it sounds, connectivity is a big issue in graph theory. The problem can also be simplified to, does there exist a path from node A to node B? In this scenario, we don't care about the minimum cost. We just want to know, can one node reach another node? A typical solution to this problem is to use a union find data structure, or do a very basic search algorithm such as a depth first search or a breadth first search. Another common problem is detecting negative cycles in a directed graph. Sometimes we're dealing with graphs that have negative edge weights and we need...
Okay, I need to go from 0 to 6. It could be whatever, right? What is the easiest and shortest way to go? This, and this. Interesting way to think. Interesting way to think.
know if a negative cycle exists, because if there does, it can throw everything up. In this graph, nodes 1, 2, and 3 form a cycle, because if you cycle through all the nodes, you end up with a cost of negative 1 if you add up all the edge weights. In fact, you can cycle endlessly, getting smaller and smaller costs. In the context of finding the shortest path, a negative cycle is like a trap that you can never escape. However, there are some contexts where negative cycles are beneficial. Suppose we are trading currencies across an exchange or multiple exchanges. Currency prices try to remain consistent throughout the day across exchanges, such as trading USD to euros or Canadian to yen. But sometimes there are inconsistencies in currency exchange prices. This makes it possible to do something called an arbitrage, which cycles through multiple currencies, exchanging one currency for another and coming back to the original currency with more money than you originally started at a risk-free gain. This is something we can use graph theory for, because it uses detecting negative cycles. There are two well-known algorithms that can detect negative...
That's quant. Finance. Use graph theory. Oh shit! It's become more and more important in finance systems on network-based models. Crazy, bro. Crazy.
Those are Bellman-Ford and for the Warsaw. Something that comes up now and again is finding strongly connected components within a graph. This is analogous to finding components of an undirected graph, but for directed graph.
Strongly connected components, CSSC, can be thought of as self-contained cycles within a directed graph. So what the fuck is this gonna do? So let's say I go here, fine, bro. But that's the thing. The root variable, the root node wouldn't start here. So let's say this is like root.
When looking at strongly connected components, we're looking for self-contained cycles within the graph, where every vertex in a given cycle should be able to reach every other vertex in that same cycle. This is very useful in many algorithms and is usually an intermediate step. So it's important to know how to find these strongly connected components. And there are many very elegant algorithms to do so, such as Cartesian algorithm. You probably won't go through your computer science career without hearing about...
Okay, interesting. Strongly connected components. Strongly connected components. SSCCS can be thought of as a self-contained cycle within a directed graph. So what if my graph started here? It'll go from here to here to here to here to here to here to here. Fucking die off. So what if my graph started? I mean, it wouldn't. I'm assuming it will start here, right? We'll go here. Again, in some algorithms. Yeah, makes sense. If it goes here, first time it will go here, second time it'll like... Even here, bro. Look at it. Yeah, what is this supposed to do? Let's say I somehow ended up here. I'm going in this direction. I don't have any nodes to go, so I'm gonna go here. I don't have any nodes to go, I'm gonna go here. Interesting. In Jujutsu, I think triangular number is the closest dilemma that it's like. In Jujutsu, you actually need this, right? Where we have like a really strong dilemma where people can't really like break out of it. Either you're getting triangled or you're getting your arm snapped in half. Interesting thing to keep in mind as we move forward.
Algorithms to do so, such as targeting example. You probably won't go through your computer science career without hearing about the traveling salesperson problem. The TSP problem is the problem of having n cities and the distances between each of them, and finding the shortest path that visits each city and comes back to the original city at minimum cost. For example, if your graph is the one on the left, a possible TSP solution is the graph on the right, which has a cost of 9. The TSP problem is NP hard, meaning it is a computationally challenging problem. This is unfortunate because the TSP problem has several very important applications. Some famous algorithms we can use to actually solve this problem are the TLDR algorithm with dynamic programming, doing some kind of branching and bounding algorithm, or you can use one of many approximation algorithms such as the
Interesting.
This next problem I want to talk about is finding bridges in a graph, which is something of a fascination to me. Bridges are edges which, if you remove, increase the number of connected components in the graph. In this graph, the edges highlighted in pink are bridges. Bridges are important in graph theory because they often hint at weak points, bottlenecks, or vulnerabilities in graph. Think of your graph as a telephone network or a set of bridges between islands. You can immediately see the usefulness of bridges. Related to bridges but not the same are articulation points, which are nodes that, if removed, increase the number of connected components in the graph. In the same graph, you can see the 3 articulation points highlighted in pink. The next problem is finding the minimum spanning tree of a graph. A minimum spanning tree is a subset of the edges that connects all the vertices together without any cycles and with minimal possible cost. So in summary,
This is the overview too.
tree, meaning it has
I'm overanalyzing the overview.
at a minimal cost. Hence why we give it a minimum spanning tree. For example, in the graph below, one of the possible minimum spanning trees is this graph with a least cost equal. Note that all minimum spanning trees of a graph have the same minimal cost, but are not necessarily identical. Minimum spanning trees are seen in lots of different applications in computer science, including designing a least cost network, circuit design, transportation networks, you name it. There's also several approximation algorithms which rely on minimum spanning trees, which is pretty interesting. If you want to find a minimum spanning tree of a graph, I recommend using one of Kruskal's, Prim's, or Baruka's algorithm. This last problem I think is the most fascinating, and it is about finding the maximum flow through a special type of graph called a flow network. Flow networks are networks where edge weights represent capacities in some sense. Capacities might be things like the maximum amount of cars that fit on a road, or the maximum amount of volume that can flow through a pipe, or even the number of boats a river can sustain without destroying the environment. And these types of flow networks, we often find ourselves asking the question, with an infinite input source, that is of cars, water, boats, whatever, how much flow can I push through the network, assuming we start at some source and try and make it to some sync node. This question is important because at some point there is bound to be a bottleneck somewhere in our flow graph that limits the amount of stuff we can have traveling on the network, making it from point A to point B. The maximum flow would then represent things like the volume of water allowed to flow through the network of pipes, the number of cars the roads can sustain in traffic, or the maximum amount of boats allowed on the river. With these maximum flow problems, we can identify the bottlenecks that slow down the whole network and fix the edges that have lower capacities. That's all the problems I want to talk about today. If I missed it,
Depth first search. Woo! Excited, bro.
problem, please.
Okay, I'm actually excited. Still excited. Let's go. Breadth first search, grid, shortest path. Should I do some breadth first search shit? Pull up neat code. Where my boy need code at? Wow, boy need code at? Last time. Should be graphs, right? But it is trees. Lot of the shit, it is trees. So I'm pretty sure he does have a lot of. Look at the people. All the people that are watching this.
Of all the shortest path algorithms in graph theory, Bellman-Ford is definitely one.
I mean, that's what I don't understand. It's like if 60,000 people watch this, and the first, if you look at the first one, it's like 1 million people watch this. You know what I mean? Not really, but usually the first couple of videos is like fucking 2 million, 7 million, 8 million, and the last videos are like fucking 20 people watching it. You know what I mean? It's like no one gives a fuck anymore. It's like I gotta learn the next thing, you know? Like I gotta fucking learn about fucking JavaScript or some shit. Yeah, this is the future, bro. It's like, yeah, no one wants to like sit and like learn from professors anymore. It's gay.
This
This is
is
the
Hello and welcome. My name is William, and
hopefully
I
I could like
contribute back.
hopefully.
today we're moving on to talking about
It's
It's gonna be in English though.
Tamil
Tamil
the
the best matter. No more Tamil on that. But this one, I'm trying to speak in
the
Tamil.
depth
Let's
first
go.
search algorithm, which plays a central role in several graph theory algorithms.
Algorithm.
A depth first search is a
Come
core
on, bro.
algorithm in graph theory that allows you to explore nodes and edges of a graph, so it's a form of traversal algorithm. The nice thing about a depth first search is that it's really easy to code, and it runs in a time complexity of big O of V plus E, that is vertices plus edges, which is directly proportional to the size of your graph. By itself, a depth first search isn't all that useful, but when augmented to perform other tasks, such as count connected components, determine connectivity between nodes, or find bridges and articulation points, the depth first search algorithm really shines. So let's look at an example. As the name suggests, a depth first search plunges depth first into a graph without regard for which edge it selects next, until it cannot go any further, at which point it backtracks and
This is how I used to like think in chess too. I used to like play a lot of chess. This is the exact way to do it too.
You
You have like chess pieces, right?
Let's
Say a move from pawn, a move from the knight, move from the my man bishop, looking like an ice cream, looking like a butt plug.
So
So this is how it actually works. Sometimes,
let's
let's say I'm thinking about a pawn move, right? I'm thinking of moving a pawn. I go really deep on it. Again, it's like a mid-game position. I go really deep on this. I go really deep on this. I go really deep on this. Pause. That shit looks like a butt plug. Pause. I think that's the best way to do it. Instead of again, these have its own branches too, which is the beauty of chess, I guess. And bro, I never like my highest rating was 1,800. Never went past that.
In
In Leeches too, which is like 1,600 on the on the real life. It's crazy.
continues its
I didn't learn any openings, so it's all creativity from my end.
It's a
It's a little bit high.
exploration. So a depth first search has to start on a node, and I'm going to start our depth first search on node 0, and now we arbitrarily pick a node to go to. So from node 0, we're going to go to node 9. Then from node 9, we only have one choice, which is to go to node 8. At node 8, arbitrarily pick an edge. So we're going to go outwards to node 7. Node 7, we have plenty of edges to choose from, so let's go to node 10 to node 11, and 11 to 7. So we don't want to revisit already visited nodes or nodes that are currently being visited, so we have to backtrack. To indicate backtracking, I'm going to label edges and nodes as gray, so backtrack all the way back to node 7. So we're not finished exploring node 7 because there are still edges to be picked, so I'm going to go to node 3. At node 3, I'm going to go to node 2. Node 2 is a dead end, so we backtrack, then go to node 4. Node 4 is also a dead end, so backtrack from node 4 back to node 3, then pick node 3's last edge to go to node 5, 5 to 6, and 6 to 7. Can't go to 7 because we're visiting 7 currently, so backtrack all the way back to node 8. From node 8, we still need to visit its last edge, which goes to node 1. Node 1 back to node 0. We can't go to node 0 because we're currently exploring it. Then backtrack all the way to 0, which completes our depth first search traversal of this graph. So this was one particular depth first search traversal, but as you saw, it could have gone a lot of different ways. So now let's look at some pseudocode for this depth first search to get a deeper understanding of how it works. The first thing we'll need to do is initialize these three variables, which are n, the number of nodes in our graph, g, the adjacency list representing the graph, and visited a boolean.
So let's pull up our trusty old VS Code. I think I already have, yeah. So nodes. I'm thinking three nodes, right? Three nodes. It being, I mean, four nodes, okay. It's being wrestling and all of that shit, right? Yeah, matter of fact, let's just like write it down. Wrestling, scrimmage, wrestling, scrimmage, and what else? We got wrestling. I was thinking about something else. Okay. What else we have? Top jutsu? No. Escapes. Attacks. Whatever. Okay. And the edges should be. No. Okay. N would be the N is equal to line of knots. Okay. How does it know what I'm about to write? It's crazy.
Array containing
And G is equal to adjacent list representing graph visited is equal to false. What?
true or false at index I depending on whether or not node I has been visited. In the beginning, this array should have all false values because we have not visited any nodes in the graph. Once that is set up, at the bottom I define our starting node to be node 0 and then call the depth first search method to do the exploration. The depth first search itself has one.
Okay. Wait. Depth first search. Do I need depth first search? Why do I need even search? That's just. Yeah, I do need to search because I just click though. You know what I mean? I just click. The next one will show up. I don't need to implement a depth first search, but let's just go with it.
Argument. The current node we are at, which I have conveniently named at. This method is recursive, so I check the base case, which is whether we have already visited.
If visited. Wait, what is visited? False? What the fuck? Bro, just source code. Let's see the source code. Could you do it in Python or some shit? I'm gonna slide up to your blood with intelligence. Pa. Fibonacci heap. Brother, just give me whatever.
If so, we have no business here and can return. Otherwise, let's visit this node by marking it as true and exploring all of its neighbors.
Oh, I see. So how do I actually populate my matrix, adjacent matrix? Do I need to import? Okay, I need to. Depth first. Talking about depth first, representing the graph adjacent matrix. Easy to check if edge exists. Uses n of what the fuck? Adjacent list is what I meant. It's based for the graph spans few edges. Easy to check if an edge exists. Easy to check, faster to iterate over neighbors. Okay, easy to just check if it exists. Okay, if it exists, it will return some sort of non-zero value. How do I actually check it? Exactly. Okay.
Yeah,
Yeah, don't just give me a non-zero value. Adjacency list. Each node has stores as a list in its neighbor. How should I actually? Whatever. Let's see what the depth first search approach
Reach
is.
into the adjacency list and pull out all the neighbors of this node and explore them.
Bro, that's like 40 of these. What the fuck?
Over each and recursively calling
Yeah.
a depth first search method. And that's all a depth first search really is in a nutshell. Let's look at another simple use case for a depth first search. I want to discuss finding connected components in a graph. First, let's understand what we mean by connected component. Sometimes a graph is split into multiple disjoint components, and it's useful to be able to identify and count these components. One way to identify these components might be to color them so we can tell them apart. But what does coloring nodes really mean to a computer? Coloring nodes is equivalent to labeling each node in a component with the same ID value. For example, every node in the purple component. Feel free to list it in the description below. Component gets an ID of 1, and every node in the green component gets an ID of 3. We can use a depth first search to identify components this way. First, make sure all the nodes are labeled from 0 to n non-inclusive, where n is the number of nodes. The basic
Should I give them? I should hard code them probably. Because why do I need depth first search?
Like
I'm trying to use the theory that I'm trying to learn, but in fact I don't have to use it.
basic algorithm is to start a depth first search at every node, except if that node has already been visited, and mark all reachable nodes as being part of the same component using the same ID. So if we start at node 0, then we do a depth first search here, and then every node in this component gets an ID of 0. So go to 8, give it an ID of 0. 14 gets 0. 13, also label it with a 0, then backtrack like you do a depth first search, then explore node 4, give it an
That's the thing with backtracking. Backtracking. Important shit.
ID of 0. And then finish exploring that component, and then move on to the next node in order, so go to node 1 next. Then node 1, sorry, depth first search there, so go to node 5, label it with a 1. 5 goes to 17, label it with a 1. Backtrack, go to 16, also label it with a 1. We're finished exploring this component. Then we would go on to node 2, wherever node 2 is, then explore that component. Then node 3, explore node 3's component, unless node 3 has already been visited, and so on. So we do this for every component, and eventually we get to label all the components, and we use a depth first search to do that. Awesome, so that's how we find connected components using a depth first search. Now let's look at some pseudocode for how we do this. First, we'll need a couple of things. We'll need everything from the previous code we looked at, so n, the number of nodes in our graph, g, our adjacency list, and our visited array. But additionally, we'll also need a variable called count that tracks the number of connected components and components. An integer array.
Want to translate. I want to use ChatGPT to translate. The shit that he has. Video slides, yeah. Script. Oh, this is a script? What the fuck? Status. Bro. A depth first search. Will it make me a better programmer? It will. It actually will. Blame? Brother. What am I looking at, brother? Just give me the code, brother. I wanna. It's really funny. Okay. Let's just think of this in a different way. Bam, bam, bam. Script. Bro, give me the fucking code. What the fuck are you doing? Give me the Java code, man. What the fuck? Fuck what you talking about? Give me the code, bro. Fucking astaghfirullah. This is actually okay. This is actually the way to do it.
That's how we find connected components using a depth first search. Now let's look at some pseudocode for how we do this. First, we'll need a couple of things. We'll need everything from the previous code we looked at, so n the number
G is equal to adjacent list representing graph is equal to 0. What?
nodes in our graph, G our adjacency list, and our visited array. But additionally, we'll also need a variable called count that tracks the number of connected components and
Bro, what am I doing? Like, just give me the normal code, bro. Could you not do this shit in Python? It's like way easier in Python, I promise. Invert a binary tree, let's go.
Input root
1, 2, 3, 4, 5, 6, 7, output. So I'm gonna go here. Here. Invert a binary tree.
Why do
I need to invert it? Output would be 1, 3, 2, 7. Oh, this thing is going here. Okay. Okay. How do I know what's... So 4 is the root, I think. 4. Okay, let's visually see what's going on. What is going on here? But which... wait. But which is connected to which? Is it like given the root of a binary tree, invert a binary tree and return its roots? So 4, 2, 4, 2, 7. How do I know which one is which? What the fuck? What the fuck? Yeah, bro. Yeah. Okay, let's just finish this one.
An integer array that holds the integer value of which component a node belongs to. Inside the find components method, we loop over every node and check if the current node has been visited or not, and then execute some logic. This depth first search variant differs slightly from the previous in that we execute a depth first search for every unvisited node. When we actually do the depth first search, we visit nodes and mark them as visited. So we never revisit the same node more than once. We either skip over a node because it's been visited in this for loop, or start a depth first search there.
Oh, I hate nuance. I hate it so much. Bro, is that an easier way to like study this shit? Is that an easier way to study this shit? Breadth first search.
What the fuck is wrong with that? What for I in range length of head minus 1? This code looks retarded. Why does it look retarded, bro? It looks so retarded.
For eye in range, length of head. Yeah, what's wrong with this? I gotta do this shit. What is a linked list? Bro, I'm learning everything right now.
We increment the count variable
It's
and
crazy.
how many depth first searches we have done. Inside the depth first search method itself, the two things we do are mark the current node as visited and set the current node to be part of the component equal to the value of count. And then components or generate mazes and many more tiers. Hello and welcome back. My name is William, and today's topic is the breadth first search graph traversal algorithm.
I'm gonna go back to linear algebra in a couple of minutes, maybe. I don't know. This is like too fucking unrelated. And honestly, don't really like need it.
Graph traversal algorithm.
I'm gonna go back to linear algebra in a linear algebra in a couple of minutes, maybe. I don't know. Should I go back to linear algebra? Fuck it, bro. Fuck it. Graph theory, I like it. I'll see another video on graph theory. Just to like kind of get the idea of it, but it's like too technical or some shit. And it's not even in Python. You know what I mean? Like, what am I supposed to do? It is beautiful. I ain't gonna lie, but it's like, how am I supposed to study something
The first time
that doesn't have Python in
the
it?
assumption was that it might be related to things like graphs or functions, as those were the only types of graphs I was familiar with at that.
Let's see my boy. Bro, the 3 blue, 1 blue, or whatever the guy name is, he has done so much shit for this math
Imagine that
community,
it has
I had to
specifically
say.
wires in the following village, so that
That's actually crazy. Like, he has like 500. Are you guys looking at this? He has like 500. What the fuck? Why is it not moving? Move. Bro, what happened? What the fuck? It has like 500 views? What the fuck? Look at this data. I do want to make
of
my...
distributing wires in the following village, so that
Bro, that's crazy. That's like 500 views. Like look at this, bro. 500 views. That's depressing. That's gonna be me. You know what I mean? That's, if I don't lock in, that's gonna be me. That's what I'm gonna do. I'm gonna do a Tamil version of all of these graphs. It's like Tamil examples and shit like that. That'll be nice. Gotta keep myself
The first time I heard about
healthy.
graph, my initial assumption was that it might be related to things like graphs of functions, as those were the only types of graphs I was familiar with at that point. But the relatively new mathematical field of graph theory turns out to be in fact something totally different. What exactly is a graph?
Okay.
A graph G is defined by a pair of a finite set capital V of nodes, also called vertices, and a set of edges capital.
I do want to check one thing before.
Okay.
How do you get done?
Capital E. The edges of a graph represent relationships between the nodes. In most cases, the nodes are labeled with numbers or alphabetical letters to distinguish them from each other. For the graph above, the set of nodes capital V is capital V equal to the set containing the elements 1, 2, 3, 4, and 5, and the set of edges capital E is defined by the following sets. The graph G is then a pair of capital V and capital E. Regarding this edge set, the graph consists of edges connecting the nodes 1 and 2, 1 and 3, 1 and 4, 2 and 3, 3 and 4, 3 and 5, and 4 and 5. A graph like this is called an undirected, unweighted graph. Before we proceed, a quick remark about the notation used in this course. An edge connecting two nodes U and V in an undirected, unweighted graph will be denoted as UV or SVU. Both notations have the exact same meaning. An incredible amount of problems in the real world can be modeled through a graph, especially when the instances of the problem stay in some relationship to each other, like in a network. Let's say an edge in this network between two individuals represents a friendship between them. By the selection of any person from this network, we can explore all of their friends by tracing where the edges connected to them led. More formally, the friends of the person in the yellow node, let's call this node U, define the neighborhood of the node U. In a general graph, the neighborhood N of U consists of all nodes V in the set capital V that are reachable from the node U by using a single edge, so an edge connecting U and V that is included in the edge set capital E of the underlying graph. Every friend of the person in the yellow node is called an adjacent node of the yellow node. Or in math language, every node contained in the neighborhood set N of U is an adjacent node of U.
Okay, let's look into this.
A
The neighborhood of U
is
N of U, and a U, and a U. Any node is adjacent to U. Okay, fair.
The last definition counts the amount of edges attached to the yellow nodes. This number is called the degree of a node.
B.
In this
Oh,
graph, the
see
degree
you
of a
again.
person
Degree.
corresponds to the number of friends the person has. But important, the degree of a node doesn't always represent the number of neighbors of a node. This is only the case if there isn't more than one edge between two nodes.
Yeah, you could have like two
Which
nodes
is
here.
obviously a degree of 5. An interesting property of graphs becomes visible when adding all degrees of all nodes in a graph together. For this, let us iterate through every node in the graph, determine its degree, and add all degrees together. This node has a degree of 6, so our total degree becomes 11. The next node has a degree of 9, so our total degree becomes 20. The next one
Yes,
Yes,
always
always
gonna
going
be
to be bigger than the
28,
entire
and so on.
nodes.
At the end we obtain the sum of the degrees of all nodes. And what property does this number have? It is even. In fact, this is not a coincidence here. Independent of the specific graph, the sum of all degrees is always even. Furthermore, knowing the sum of all degrees in the graph allows also for the calculation
Shit, bro.
Shit.
Shit. 3 blue, 1 brown. Is this neural network deep learning? Okay. To graph producer implicitly every deep learning model CNN. All rely on at the computational level, but only but a fraction fundamental computational graph very important. Every framework like PyTorch, TensorFlow represents models as computational graphs, edges and nodes. Okay. Applied level graph structure specialization. Will it like a summary class? Fundamental under the hood deep learning, but it is in practice it's specialized. You only need if your data as a graph, molecules, networks, knowledge. Okay. Yeah, it's like pretty specialized, isn't it? Okay. It's pretty specialized, but why not?
Of the total number of edges in that graph, what might sound surprising at first. The summation of all degrees in the graph in the animation yields 3192. In fact, the graph in the animation is a complete graph.
Wait. So that means
it's like
no one like. Bro, isn't that crazy? Okay. Graph theory. Graph theory.
Meaning a graph in which every node is connected to all other nodes excluding itself. More detailed, this graph has 57 nodes and every node is connected to 56 equal to 57 minus one other nodes. Therefore the sum over all degrees here is equal to 57 times 56. And the total number of edges in this graph is given by half this number, because by summing up all degrees one counts every single edge twice. This lets us to suspect that the sum of all degrees in the graph is always equal to twice the number of edges in the graph. And this is in fact exactly the case. It holds the following formula. The right hand side of this equation is equal to twice a number, which is obviously even because it's divisible by 2. Now since there's an equality sign in the middle, the left hand side is...
Is that true?
So
let's say... One, two, three, four, five, six. Seven. What's the fuss about it, eh? I can only go once. Maybe that. I'll do like single arrow to represent event once.
I mean,
it kind of checks out, but I don't really see the point.
Furthermore, if you consider having n many nodes v1 to vn in a graph, this implies that the sum of all degrees is even. And the left-hand side can only be even under certain circumstances, for instance if all degrees are even or if exactly 2 nodes have an odd degree. But if the number of nodes with an odd degree is, for example, 1, it follows immediately that the total sum cannot be even. What I want to say is that the number of nodes with an odd degree in the graph is always even because the sum over all degrees has to add up to an even number according to the above formula. And the interesting implication now is that this holds for every graph. A corollary from this is the handshake lemma, which tells you if there is a party of people who shake hands, the number of people who shake an odd number of other people's hands is even. Observations like this that helps us to better understand the structure of graphs are very important in graph theory. And for some certain graphs there are indeed still many unsolved mysteries waiting to be solved. Very important in graph theory are so-called graph traversal algorithms, which aim to explore how to process every node in a graph. The range of application of
GNN.
of such algorithms is
Is
Is this GNN?
What is
What is GNN?
It's very large, and there are basically two commonly used different types of them. The one algorithm starts at a node and systematically visits all of its neighbors.
Yeah,
Then
yeah,
it
yeah.
proceeds by visiting the neighbors of the nodes that have been visited first, leading to a layer-by-layer exploration of the graph. This algorithm is known as the breadth-first search (BFS) algorithm. The subgraph generated by this algorithm is known as a BFS tree, which offers valuable information about the underlying graph. For instance, shortest paths from the starting node to all other nodes, if the length of a path is characterized by the number of its edges. In contrast to that, the other algorithm follows the approach to explore the graph in depth first. It selects in every iteration a neighbor node, possibly
Oh,
a
yeah.
neighbor,
It's
and
fucking
closes it
retarded.
out, and continues in this way until it gets stuck. In the natural way out, think about a maze is to backtrack to the last node with unvisited nodes in its neighborhoods. This algorithm is known as the depth-first search (DFS) algorithm. The resulting subgraph, the DFS tree, looks a bit familiar to a maze. And indeed, with the right modifications, this simple algorithm can also be used to generate a maze. As seen in the animation, the white rectangles are the nodes and the dark gray rectangles are the edges of this graph. I will put now a white rectangle behind this graph to make things easier to see. The only thing to do now to create a maze is to run the DFS algorithm on this graph.
The tricky bit is getting to this one, I think. Or maybe not. There's some spaces over there.
Note
Ah,
that through the
yeah.
application of DFS, this maze has a solution, since DFS calculates
That's
the
like a
path from the
brain.
starting node to all nodes in the graph. In other words, there is a path from the starting node to any other node here. In a city, it is important that every village has access to electricity. The distribution of the electricity
Guys, quick reminder. It's so, இது பண்ணது எல்லாம் யாரும் பார்த்தீங்கன்னா it's white people. We need to give a round of applause. Because man, like fucking black dudes ain't doing this, you know what I mean? It's all like white dudes, man. It's all white dudes and it's Indians, you know. White dudes and Indians. I've yet to see a black engineer. Crazy. I saw one in a convention before, but
as
other
can
than
be
that,
visualized using
Never
never
seen
seen
before.
before.
Furthermore, one can search for subgraphs in this graph such that every village in the city has exactly one access to electricity. Such subgraphs of a graph have to contain obviously every village and are called spanning trees. In the real world, each edge would be assigned a label representing the costs associated with distributing wires along the corresponding edge, which represents a street. The general goal then should be to minimize the costs for the distribution of wires such that every town gets access to electricity.
So what should I use? Okay, how do you look at it?
A
A breadth first approach could be.
Therefore, one would search for a minimum
That's
spanning
what-
tree
yeah,
in the given graph, which is a spanning tree with the least possible total cost. Very important in graph theory, especially in the era of navigation systems like Google Maps, are shortest path algorithms. Think about a map of a country where each node represents a city and the edges are labeled with costs such as the kilometer distances between two nodes or the duration to travel between two adjacent nodes. Now imagine that you are a pizza delivery guy tasked with delivering a pizza to a client located far away. In this scenario, choosing the shortest route with respect to the edge labels is crucial to ensure that the client doesn't have to wait too long to receive his order. These were just a few examples of graph theory problems that we will analyze throughout this course, which hopefully gave you a glimpse.
Again, I think Google Maps allow. I think we use triangulation method in Nekra. I'm not really sure though. They draw triangles. Let's say this is the fucking. This is the world, right? The Chennai. Pizza order பண்றான். They use like small little triangles to like approximate the distance. I think. I'm not sure. Not sure. Just making it up as I go. Let's go.
Of a feeling of what graph theory problems are about. In fact, we've seen that graph theory is a very strong and broad field in mathematics with various practical applications. But despite its current significance, this field is relatively new. To understand the origin of graph theory, we have to go back in time to 1736. In the center, there's nobody else than Leonhard Euler, who probably doesn't need any further introduction due to his...
Bro, it's like relatively new. That's even the crazy thing. Graph theory is fucking new. Isn't that crazy?
The most famous mathematical formulas. Euler lived nearly in the same time span as the two outstanding mathematicians Gottfried Leibniz and Isaac Newton. These two mathematicians are probably among the most famous and influential mathematicians to have ever lived on this planet. In the time around the year 1735, the citizens of a Prussian city named Königsberg, which was not far from St. Petersburg, the home of Leonhard Euler, used to spend Sunday afternoons walking around their beautiful city. While walking, the citizens decided to create a game for themselves, their goal being to devise a way which they could walk around the city, crossing each of the 7 bridges in Königsberg exactly once. Even though none of the citizens of Königsberg could create a route that would allow them to cross each of the 7 bridges exactly once, the question whether this is even possible remained unanswered.
Yo, this guy, this motherfucker, Euler, he can't even see, man. He's like a fucking pirate out here. Crazy. Can't even see.
For them, it didn't last long before Leonhard Euler was confronted with this question.
I need to fact check though. This Euler. Fuck. Blind. Question mark. Bro, it's crazy. Almost completely blind. Later it's like later in life, of course.
Euler worked on complicated and complex problems, so one could have assumed that he wouldn't invest time in a problem seemingly so unrelated to the field of mathematics. But there is a certain property about this problem that piqued Euler's curiosity. Euler's letters to other mathematicians revealed his fascination for this problem. The aspect was the problem's underlying structure, and Euler noticed that solving it didn't require specific details about the bridges or landmasses. Instead, he realized that the problem could be abstracted, leading him to set the foundation for a concept that is known today as graph theory. Furthermore, he referred to this problem as being in a field mentioned by Gottfried Leibniz called Geometria Situs, the geometry of position. A way to abstract such a problem as the 7 bridges of Königsberg problem can be illustrated using a simplified model with 4 islands and 7 bridges. Every island represents obviously a node and every bridge an edge. A walk of a citizen in Königsberg has also a name in graph theory. It is a walk in the underlying graph, translating to a sequence of adjacent nodes in the graph. While we try to walk through this graph and to cross every edge exactly once, we will always face the problem that at some point we will get stuck at the nodes, because we won't have any unused edges left to take anymore. However, this will always be necessary since we will still have other edges left that we have to visit. In fact, it doesn't even matter which walk you take here, because you will never succeed. But why? In very simple terms, this has something to do with the degrees of the nodes in this graph. Is it guaranteed in this graph that if one edge leads to a node and...
Wait. I was looking at... Yeah, the same thing. Bro, that's crazy. Okay, amazing. Walk through. Could you even do this? Nah, it's impossible.
Another edge will let out of that node again. Very soon you will see an explanation for this. But before we start dealing with the analysis of such
Oh, you
You just have like a.
we should
I think I know it.
You
You just have to do one of these
bomber
clock moves
where
where you go
twine,
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 twine.
twine.
Oh
Oh
shit.
shit.
Maybe
Maybe here.
Or you
Or
can
you can start from
here,
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 here. Maybe no, I don't give a fuck. Bro, I remember.
give them a name. Fundamental definitions in graph theory are definitions of a path, a cycle, a trail, a circuit, an Euler trail, and an Euler circuit. Many people get confused here, therefore it is very important to consider these definitions very clear. Starting with a path is a walk in a graph such that all visited nodes in the walk are distinct. So in the general definition of a path, it is not allowed to use nodes more than once. A cycle is a path that is closed, meaning it starts and stops at the same node. Furthermore, the length of a cycle is given by the number of used edges in the cycle. A trail is a walk such that all used edges are distinct. Furthermore, it can visit nodes more than once. A circuit, not to confuse with a cycle, important, is a closed
It's a loop.
Yeah.
Ah,
Ah.
whoever like
discovered
scored this shit, bro.
You're
You're
crazy.
crazy.
And now the point where many people get confused. An Euler trail is a trail that visits each edge in the corresponding graph exactly once. While such a trail is often referred to as an Euler path, it basically isn't a path because it can visit nodes more than once. These definitions are unfortunately not always consistent. If you hear people talking about an Euler path, it's very likely that they mean an Euler trail, as the term Euler path has become established. And now the last definition, the definition of an Euler circuit. An Euler circuit is a circuit that visits each edge in the graph exactly once.
So let's take it back.
All used edges
Lot of jujutsu is somewhat of a cycle, you know. You're coming. You could. Interesting. I never thought about it like that. So you mean? Bro, I never thought about it like that. It's crazy. Okay.
Let's
Go back.
It's
It's not actually.
Okay,
So we have a path.
Everything
Everything's like a distinct,
right?
right?
Different.
Different.
That's
That's the path.
And
And we have the cycle.
It's a
It's a
closed.
closed.
It's
It's a cycle. It comes back
to
to the.
It's
It's
closed,
closed, right?
are distinct. Furthermore,
All edges are distinct. What the hell, bro?
it can visit nodes more than once.
All the nodes, different edges would be. I mean, trail would be. Yeah. One direction. I mean,
that's
the trail.
Okay.
Okay, path is like one direction and trail is like whatever.
It
It is a closed trail.
That's
That's
the
the
circuit.
circuit. Euler's path.
What is
What is
Euler?
Euler?
Visit nodes more than once. These definitions
It's a trail that visits each edge exactly once. So that's a path. So that's a path, broski.
While such a trail is often referred to as an Euler path, it basically isn't a path because it can visit nodes more than once. These definitions are unfortunately not always consistent. If you hear people talking about an Euler path, it's very likely that they mean an Euler trail, as the term Euler path has become established. And now the last definition, the definition of an Euler circuit. An Euler circuit is a circuit that visits each edge in the graph exactly once. What we are searching in Königsberg is either an Euler circuit or an Euler trail. What one can observe immediately is that the graph in the bottom right corner here, which contains an Euler circuit, has only nodes with an even degree. And in fact, a graph that contains at least one node with an odd degree.
Okay. I kinda get it. Euler circuit is a circuit that only visits each edge exactly once. It's okay. This is just like a trail. That means like a what? Yeah, the nodes doesn't matter. And the edges could be... Yeah, the edges don't really matter. Okay.
Degree cannot have an Euler circuit. The explanation for this is also not very deep. If you try to start your Euler circuit with a node that has an odd degree, for example a node with a degree of 3, then you will leave the node at the beginning, traverse somehow through the graph, come back to the starting node at some point, and if you leave it then once again, you won't be able to return to this node anymore as required for an Euler circuit. Otherwise, if you start your Euler circuit with a node with an even degree and encounter a node with an odd degree during your traversal, you will be forced to use all of its adjacent edges during your route, and then you will get stuck. Furthermore, Euler's results in this context can be found in literature by searching for Euler's path and circuit theorems, or just by searching for Euler's theorems. Euler shouts the three following assertions. Assertion 1, a graph in which all nodes have an even degree has an Euler circuit. Assertion 2, a graph with exactly two nodes of odd degree contains an Euler trail, but not an Euler circuit. And assertion 3, a graph with any number of odd nodes other than 0 or 2 will not have any Euler trail. We've already discussed the first part of the proof for assertion 1 of this theorem. If you're interested in more, I encourage you to try to prove or to argue why the other assertions must hold. Consider
a graph with exactly two nodes of odd degrees, an Euler trail, but not an Euler circuit. A graph with any number of odd nodes other than 0. Okay, let's actually draw. Okay, let's draw a graph with two nodes of odd degree contains.
During the last statement, and our graph in the 7 bridges of Königsberg problem, we can observe immediately that all nodes have an odd degree, implying that this graph has neither an Euler circuit nor an Euler trail.
It's like a proof, okay. If it's an odd... What does it have to do with anything, honestly? Let's say it has like 5 edges, right? This should have like 5 edges. Well, what does it have to do with anything? If it's like let's say 4 edges. Let's say this one doesn't really exist. Can the circuit be closed? Here. No. Here. I'm pretty sure you can do it. I think I did it on... Yeah. So the circuit makes sense. If any number of grad odd number less than 0 or 2 will not have an Euler. If a graph with exactly 2 nodes of odd degree contains an Euler, exactly 2 nodes of odd degree contains an Euler trail. A graph all nodes have even degree contains Euler circuit. But that's the thing. This will be 2.
this
This
will
will
be
be
4.
4.
Still
Still has a
Euler
Euler circuit.
Right. Goes
Goes
here.
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 I mean,
no. It's
it's
4
4
and 2. This one
doesn't exist.
So it
So it goes
here,
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 here.
here.
Bro,
I just did it like 2 seconds ago. What the fuck?
Okay, here,
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 here.
I need
I need to start from here, I think. Yeah. It doesn't actually exist. So let's say this is 2 again.
Let's cut
Let's cut this shit up.
It
It goes from
here,
here,
here.
here.
Okay.
Okay. Obviously,
this
this will be 3 now. This will be 2. Okay.
Makes
Sense, I think.
From 1736 to now, graph theory has undergone significant development. Various types of graphs have been born, and graph theory has found application beyond mathematics, especially in computer science. In the following, we will explore some important types of graphs, and especially their roles in data structures. Basically, graphs in graph theory can be classified into 4 classes. Undirected unweighted graphs, graphs where edges have no direction and no associated weights. Directed unweighted graphs, graphs where edges have a specific direction but still no weights. Undirected weighted graphs, graphs where
Yeah.
graph is often referred K-1 word for its beauty and complexity. It's captivating to see how such a simple concept can evolve into a captivating piece of mathematical art, where every new connection adds depth to the overall structure. But don't worry, there are still many other important and beautiful graphs that we will explore. Another important graph is, for example, the Euler graph, which is a graph where every node has an even degree, ensuring the existence of an Euler circuit.
What's the
Also
reason
an
of that?
important kind of
Like,
graph is the Hamilton
It's
graph,
a
which is a
Hamilton
graph
graph.
that contains a Hamiltonian cycle, a cycle that visits each node exactly once.
பார்க்க அந்த மத்தி பட்டி மாதிரி தான் அந்த ஒரு ரூபாய் மத்தி பட்டி மாதிரில பார்க்க
Finding such a cycle is a challenging problem, as we will see in the next video. If you deal with graph theory, you won't be able to avoid bipartite graphs. A bipartite graph is defined as a graph whose nodes can be divided into 2 disjoint sets in such a way that no 2 nodes within the same set are adjacent. In this graph, we have a partition into red and blue nodes, and none of the red or blue nodes
Bro, I'm actually surprised graph theory isn't used in neural networks. Why not? Like, but exclusive, you only specialize in GNN and reasoning
and
molecules. Interesting. Useful depending on specialization, other probability and statistics. Linear algebra is the king of all kings. Everyone knows this.
to nodes of the same kind.
whatever. Yeah, we know it.
Color. The only connection
Baptide,
in this
that's
graph are
cycles.
between the red and the blue nodes. This is a bipartite graph without cycles. Important to note is that the graph with cycles can also be bipartite. Furthermore, a graph is in general bipartite.
So where is my fucking pen? Fucking pen, bro. What kind of graph is Jujutsu moves? What kind of... Nice angles.
It is
a directed graph.
Okay.
Bro, now I'm getting somewhere. Okay. Oh shit.
I've
I've
heard
heard of it.
Don't
Don't
really
know what it means.
Back
through
propagation
propagation
calculus,
calculus, large language models. Directed graph of BJJ consists of directed graph, obviously, weighted,
gets
directed and weighted.
And
And what else?
State of mission
Markov chain.
And
You need to look at the Markov chain later. Hierarchical graph tree like, yeah. And it's all a tree-like structure.
And
And Markov chain.
Okay,
let's finish
Between
this.
the red and the blue nodes. This is a bipartite graph without cycles. Important to note is that the graph with cycles can also be bipartite. Furthermore, a graph is in general bipartite if and only if every cycle. The game chess is one of the oldest and most popular board games in the world.
I accidentally clicked it.
Of the red or blue nodes are connected to nodes of the same color. The only connections in this graph
Bipartite graph examples. It's gonna show it
are
anyway.
between the red and the blue nodes. This is a bipartite graph without cycles. Important to note is that a graph with cycles can also be bipartite. Furthermore, a graph is in general bipartite if and only if every cycle is even. This means that every cycle in the corresponding graph has to consist an even number of edges. Of course, the concept of partitioning the nodes of a graph into such sets can be generalized. For example, consider a tripartite graph.
Tripartite? Looks like a guitar chord, you know? Yeah. It's like a guitar chord. Whatever.
Note that it is not necessary for a graph to be connected, meaning that not every node in a graph has to be reachable from an arbitrary node. A graph can be made up of many connected components. A forest describes a collection of trees. Trees are graphs that have always the minimum number of edges necessary for connectivity. A tree will be typically illustrated with a structure like this. Specifically, this here is a binary tree. Visualized in this way, a binary tree can be divided into layers. On each layer or depth there are nodes, and the number of layers -1 represents the height of the binary tree. The crucial characteristic of a binary tree is that each node has at most 2 children. In addition, each node belongs to a specific class of nodes. The top node of a binary tree, known as the root node, has no parent node. A node in the tree that has at least one child is called an inner node. A half-leaf is a node that has only one child, and a leaf node is a node that has no children. Another important type of a tree that is similar to the binary tree is the ternary tree, in which each node can have at most 3 children. But let us focus here on binary trees. Binary trees are used in various applications, for instance to visualize the execution of many recursive algorithms. Here, for example, the execution of a recursive function that calculates the 8 Fibonacci number.
Yeah.
Such that all elements to execution. If we add a new
Binary tree not
is
really
the
interested in
so-called
that.
leaf, is a simple data of the BFS algorithm is the queue. A queue is a data structure that follows the principle of adding elements to one end and removing them from the other. The 2 main operations for a queue are the linked list, or rather the so-called doubly linked list. A doubly linked list enables immediate access to the first and last element via the head and tail pointer.
Whoa.
Each element, so each cell, consists of a so-called key
Someone
value.
hacked me.
Here the number is stored in the rectangles. And also a pointer to the
Linked list is kind of like, okay.
previous element in the list, and another one to the next element in the list. Binary trees come now into play when it comes to the time complexity of basic operations such as each element, so each cell, consists of a so-called key value. Here the number is stored in the rectangles. And also a pointer to the previous time, while deleting it must be
Okay, just explaining.
searching, for example, for the node with children must be black.
It's not really interesting.
The game chess is one of the oldest and most popular board games in the world.
I think
I can like relate to this.
Guys,
100 and
1,008 rating, by the way. So I can give my nuanced opinion on this video.
It's a 2-player game where each player controls 16 distinct pieces, each of which can
Yep.
only move according to very specific movement rules.
Fact
Fact
check.
check.
We will primarily focus on one specific piece, called knight. The knight follows a very interesting movement rule. It can move in what are called L-shaped moves, meaning it can only move 2 squares in one direction and then 1 square perpendicular to that.
True. Very
Very
true.
true.
An interesting
I think
I think I'm almost done.
I don't
I don't want to watch this, if I'm being honest.
2
2
hours.
hours?
Fuck
Fuck what you talking about, man.
1 square perpendicular to that.
True. Let me like write some shit down. before we go.
Yeah, I think
I
I might come back though.
I'm
I'm gonna eat some shit
and
and
come back
back
and do
into
some linear
algebra.
algebra.
Maybe not.
Linear
Linear algebra on the side.
I'll
I'll just do a linear algebra now.
Why not? Let's
Let's
look
look
at
at the orthogonal
and
of
subspace.
subspace.
Let's
Let's do it now.
I'm
I'm gonna keep all the problem solving
to
to
myself,
myself, my own.
free time.
Okay, cameras are rolling. This is lecture 14, starting a new chapter. Chapter about orthogonality. What it means for vectors to be orthogonal. What it means for subspaces to be orthogonal. What it means for bases to be orthogonal. So 90 degree. This is a 90-degree chapter. So what does it mean? Let me jump to subspaces, because I've drawn here the big picture. This is the 1806 picture here, and hold it down, guys. So this is the picture, and we know a lot about that picture already. We know the dimension of every subspace. We know that these dimensions are R and n minus R. We know that these dimensions are R and m minus R.
Yeah.
What I want to show now is what this figure is saying, that the angle, but the figure is like just my attempt to draw what I'm now going to say, that the angle between these subspaces is 90 degrees. And the angle between these subspaces is 90 degrees. Now I have to say, what does that mean? What does it mean for subspaces to be orthogonal?
So null space.
I
I still can visually like say what a null space is.
That's
annoying.
But
But anyway,
let's go.
But I hope you appreciate the beauty of this picture, that those subspaces are going to come out to be orthogonal. Those two and also those two. So that's like one important point to step forward in understanding those subspaces. We knew what each subspace was like. We could compute bases for them. Now we know more, or we will in a few minutes. Okay, I have to say, first of all, what does it mean for two vectors to be orthogonal? So let me start with that.
Two
Two
vectors.
vectors, easy.
The word orthogonal is just another word for perpendicular. It means that in n-dimensional space, the angle between those vectors is 90 degrees. It means that they form a right triangle. It even means that, going way back to the Greeks, that this triangle, a vector x, a vector y,
Greeks are gay.
Everyone
in Greek is gay.
and the vector x plus y, of course, that'll be the hypotenuse. So what was it the Greeks figured out? And it's neat. It's the fact that so these are orthogonal. This is a right angle. So let me put the great name down, Pythagoras.
Ooh,
What am I looking for? I'm looking for the condition. If you give me two vectors, how do I know if they're orthogonal? How can I tell two perpendicular vectors? And actually, you probably know the answer. Let me write the answer down. Orthogonal vectors, what's the test for orthogonality? I take the dot product, which I tend to write as x transpose y, because that's a row times a column, and that matrix multiplication just gives me the right thing, that x1, y1 plus x2, y2, and so on. So these vectors are orthogonal if this result, x transpose y, is 0. That's the test. Okay. Can I connect that to other things? I mean, it's amazing. It's just beautiful that here we're in n dimensions, we've got a couple of vectors, we want to know the angle between them, and the right thing to look at is the simplest thing you can imagine, the dot product. Okay, now why? So I'm answering the question now, why? Let's add some justification to this fact that that's the test. Okay, so Pythagoras would say we've got a right triangle if that length squared plus that length squared equals that length squared. Okay, can I write it as x squared plus y squared equals x plus y squared? Now please don't think that this is always true. This is only going to be true in this, it's going to be equivalent to orthogonality. For other triangles, of course, it's not true. For other triangles, it's not. But for a right triangle, somehow that fact should connect to that fact. Then we just make that connection. What's the connection between this test for orthogonality and this statement of orthogonality? Well, I guess I have to say, what is the length squared? So let's continue on the board underneath with that equation. Give me another way to express the length squared of a vector. Let me just give you a vector. The vector 1, 2, 3. That's in 3 dimensions. What is the length squared of the vector x equal 1, 2, 3? So how do you find the
X equal to 1.
What is the length squared of the vector x equal 1, 2, 3? So how do you find the length squared? Well, really, you want the length of that vector that goes
Square it, right?
up to and out 3, and we'll come back to that right triangle stuff. The length squared is, this is exactly x transpose x. Whenever I see x transpose x, I know I've got a number that's positive. It's a length squared, unless x happens to be
Isn't that I?
That's the one case where the length is 0. So, right, this is just x1 squared plus x2 squared plus so on plus xn squared. So in the example I gave you, what was the length squared of that vector 1, 2, 3? So you square those, you get 1, 4, and 9, you add, you get 14. So the vector 1, 2, 3 has length 14. So let me just put down a vector here. Let x be the vector 1, 2, 3.
Yeah.
So we'll get
Whatever.
2 and minus 1 making 1, 3 and 0 making 3. And the length of this squared is 9 plus 1 plus 9, 19. And sure enough, I haven't proved anything, which is true, right? 5 with 19. X plus. This is going to be true when we have a right angle. And let's just...
So x could be written as
x transpose.
I mean y could be written as x transpose. I can understand
And
that.
this is x plus y transpose x plus y. Okay. So I'm looking, again, this isn't always true. I repeat. This is going to be true when we have a right angle. And let's just...
Oh, we never
We
have
never
a
have a triangle.
simplify this
Okay.
stuff here. There's an x transpose x there, and there's a y transpose y there, and there's an x transpose y, and there's a y transpose x. I knew I could do that simplification because I'm just doing matrix multiplication and I've just followed the rules. Okay, so x transpose x is cancel, y transpose y is cancel, and what about these guys? What can you tell me about the inner product of x with y and the inner product of y with x? Is there a difference? I think while we're doing real vectors, which is all we're doing now, there isn't a difference. There's no difference. If I take x transpose y, that'll give me 0. If I took y transpose x, I would have the same x1 y1 and x2 y2 and x3 y3. It would be the same. So this is the same as that. This is really, I'll knock that guy out and say 2 of these. So actually, this equation boiled down to this thing being 0, right? Everything else canceled, and this equation boiled down to that one. So that's really all I wanted. I just wanted to check that Pythagoras, for a right triangle, led me to this.
Interesting.
Now, no problem. To x transpose y equals 0 as the test. Fair enough. Okay. You knew it was coming. The dot product of orthogonal vectors is 0. It's just, I just want to say that.
The dot product of okay. Interesting. What does that mean? Okay, it kind of helps the graph, I think. Okay.
That's really neat. It comes out so well. All right. Now, what about, so now I know what it means when two vectors are orthogonal. By the way, what about if one of these guys is the 0 vector? Suppose x is the 0 vector and y is whatever. Are they? Sure. In math, the one thing about math is you're supposed to follow the rules. So,
I mean, y would be, if x is in the 0 vector, doesn't really change anything, does it?
If x is the 0 vector, you're supposed to take the 0 vector dotted with y, and of course you always get 0. So, just so we're all sure, the 0 vector is orthogonal to everybody. But what I now want to speak about is subspace. What does it mean?
Okay. I understand what he means. Okay.
For me to say,
he's saying like, no matter it is not a right triangle. Will the subspace we have x, y? Will this or let's completely move this shit. Maybe it's like he means this. The vector is landing on here. And it's not
like
a perfect right triangle,
will it
will
be
it be
0?
0? Will
This
this
be
be
0?
0?
It
Will because why?
I mean,
There's some mathematical proofs to it. But let's see what he has to say.
That some subspace is orthogonal to some other subspace. Okay, I've got to write this down because we're defining definition of subspace S is orthogonal, so
Yep.
to subspace, let's say T. So I've got a couple of subspaces. And what should it mean for those guys to be orthogonal? It's just a sort of what's the natural extension from orthogonal vectors to orthogonal subspaces? Well, and in particular,
So
this is how the subspace will look like. And these needs to be like fucking 90 degrees, I think.
How
is that possible? I don't know.
let's think of some orthogonal subspaces, like this one. Let's say in 3 dimensions. So the blackboard extended to infinity, right, is a subspace, a plane, a two-dimensional subspace. It's a little bumpy, but anyway, think of it as a subspace. Let me take the floor as another subspace. Again, it's not a great subspace. MIT only built it like so-so, but and I'll put the origin right here. So the origin of the world is right there. Okay. Thereby giving linear algebra its proper importance in this. Okay, so there's one subspace, there's another one, the floor. And are they orthogonal? What does it mean for two subspaces to be orthogonal? And in that special case, are they orthogonal? All right, let's finish this sentence. What does it mean? Means. We have to know what we're talking about here. So what would be a reasonable idea of orthogonal? Well, let me put the right thing up. It means that every vector in S is orthogonal to, what am I going to say? Every vector in T. That's a reasonable, and it's a good definition for two subspaces to be orthogonal. But I just wanted to see, what does that mean? So answer the question about the blackboard and the floor. Are those two subspaces, they're two-dimensional, right? And we're in R3. It's like the xz plane or something and the xy plane. Are they orthogonal? Is every vector in the blackboard orthogonal to every vector in the floor? Starting from the origin right there. Yes or no?
Probably, yeah.
So the question is,
in the Maura, again.
This is the thing. You on the border, you on the floor. You on the border, you on the floor. Every vector meaning this one. Is it
orthogonal?
Is
all of these are like orthogonal?
The board.
And the answer is yes.
Yes, it is.
Probably get some yeses and some no's. No is the answer. They're not.
What the fuck, bro? Fuck me up. Fucking old ass bitch. Nah, sorry.
No.
Whatever.
You can tell me a vector in the blackboard and a vector in the floor that are not orthogonal. Well, you can tell me quite a few, I think. Maybe, like, I could take some 45-degree guy in the blackboard and...
Okay. It's a three-dimensional space.
Not
a two-dimensional one. So
it's like
this vector and it's colored this way. And we're taking this one. So you could like be here. This could be here. Know what I mean? Doesn't have to be orthogonal.
It's
three-dimensional. Okay.
Thing in the floor? There aren't at 90 degrees, right? In fact, even more, you could tell me a vector that's in both the blackboard plane and the floor plane, so it's certainly not orthogonal to itself. So, for sure, those two planes aren't orthogonal. So what would that be? So what's the vector that's in the blackboard in both of those planes? This guy running along the crack there, where the intersection. A vector, look, if two subspaces meet some vector, well then for sure they're not orthogonal, because that vector is in one and it's in the other, and it's not orthogonal to itself, unless it's zero. So orthogonal, for me to say these two subspaces are orthogonal, first of all, I'm certainly saying that they don't intersect in any non-zero vector. But also, more than that, just not intersecting isn't good enough. So give me an example.
Non-zero vector. It is not intersecting in a non-zero vector. So என்ன சொல்ல வரானா origin இந்த intersection நடக்கணும்னு சொல்ல வராரு. This is not the origin. Not the origin. If it's the origin, whatever. Fair game.
Well, When do we have orthogonal subspaces in the plane? Yeah, tell me in the plane. So we there aren't that many different subspaces in the plane. What do we got in the plane as possible subspaces? The zero vector, real small, a line through the origin, or the whole plane. Okay. Now, so when is a line through the origin orthogonal to the whole plane? Never, right? Never. When is a line through the origin orthogonal to the zero subspace?
When is the line through an origin zero subspace?
Could
happen.
Oh, right. When is a line through the origin orthogonal to a different line through the origin? Well, that's the case that we all have a clear picture of. The two lines have to meet at 90 degrees. They have only the... So that's like the simple case I'm talking about. There's one subspace, there's the other subspace. They only meet at 0, and they're orthogonal. Okay. Now, so we now know what it means for two subspaces to be orthogonal, and now I want to say that this is true for the row space and the null space. Okay, so that's the neat fact. So row space is orthogonal to the null space. Now, how did I come up with that? But you see the like expression. That means that these subspaces are just the right things. They're just cutting the whole space up into two perpendicular subspaces. Okay, so what? Well, what have I got to work with? All I know is the null space. The null space has vectors that solve a x equals 0. So this is a guy x. X is in the null space. Then ax is 0. So why is it orthogonal to the rows of a? If I write down ax equals 0, which is all I know about the null space, then I guess I want you to see.
Okay, I'm just going to save this for tomorrow. Linear algebra. Graph theory. Signing out. Bam, 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 bam.